Hello! In this presentation, I'll be discussing particle swarm optimization, or PSO, an exciting optimization technique inspired by nature. We'll explore how PSO works, its real-world applications, and how it compares to other optimization methods. Here's a brief outline of today's presentation. We'll begin with an introduction to optimization, then move on to explore PSO, its structure, and a real-world problem it solves. Finally, we'll compare it with other algorithms and conclude with its future applications. Optimization is the process of selecting the best solution from a set of available options. The goal might be to minimize costs, improve performance, or make efficient use of resources. To do this, we control certain variables while respecting constraints. Optimization is a core technique in various fields, from engineering to finance, helping solve complex problems with limited resources. Optimization helps us solve problems by finding the best solution from a range of possibilities. By adjusting variables such as cost, time, or resources, we aim to reach an optimal outcome, considering constraints like budget limits or time frames. Whether you're designing products or allocating resources, optimization plays a vital role in improving performance. Optimization is crucial in many industries. In engineering, it ensures efficient product designs or resource allocation. In finance, it helps maximize returns while minimizing risk. Healthcare providers use optimization to manage staff, equipment, and resources to ensure patients get the best care with minimal waiting times. In energy management, optimization is used to balance electricity supply with demand. In the supply chain, it's about finding the most efficient delivery routes, saving costs and time. Manufacturing relies on optimization to reduce waste and improve production efficiency, ensuring resources are used to their full potential. Linear optimization handles straightforward relationships between variables commonly found in resource allocation. Nonlinear optimization is used for more intricate systems where variables interact in complex ways. For larger, more complicated problems, metaheuristic techniques like particle swarm optimization are employed. These methods mimic natural behaviors, such as how birds flock or fish school to find food, making them effective in solving large-scale, real-world issues.
Metaheuristic algorithms are designed to solve complex problems by exploring vast search spaces. Unlike traditional optimization techniques, which can struggle with large or poorly defined spaces, metaheuristics use intelligent strategies to search for solutions. While they don't guarantee the perfect answer, they often find solutions close to optimal, making them valuable in solving real-world problems. Examples of metaheuristic algorithms include genetic algorithms, which mimic natural selection by evolving solutions over time. Simulated annealing, on the other hand, uses probabilistic methods to escape local minima and gradually find better solutions. Ant colony optimization simulates how ants find optimal paths to food, using pheromone trails as a way to guide the search for efficient solutions. Metaheuristic algorithms are ideal for large, complex problems where traditional techniques fall short. These algorithms are highly flexible, capable of navigating nonlinear, multimodal landscapes, and they adapt easily to various problem types. Instead of getting stuck in local optima, metaheuristics continue exploring, allowing them to find solutions quickly and efficiently, even for problems where other methods may fail. Swarm intelligence refers to the collective behavior of groups, such as birds or fish, that work together to solve complex problems. These decentralized systems exhibit intelligent behavior without a central control, relying on local interactions to achieve global optimization. This concept inspired algorithms like particle swarm optimization, where multiple agents or particles work together to find solutions. Particle swarm optimization is modeled after natural phenomena like bird flocking or fish schooling. Just as birds move together, adjusting their direction based on the group, particles in PSO adjust their position based on their experience and the experience of others. This enables them to explore a solution space efficiently. searching for the best possible solution. PSO differs from other optimization algorithms like genetic algorithms or simulated annealing. Instead of using evolutionary concepts like crossover and mutation or relying on probabilistic decisions, PSO uses simple rules based on collective intelligence. Particles share information, learning from the best solutions discovered by others, which allows them to converge toward optimal solutions faster. PSO has widespread applications. In engineering, it's used for optimizing complex systems like structural design. In healthcare, it helps in resource allocation, ensuring that treatment plans are as efficient as possible. Financial institutions use PSO to optimize portfolios, balancing risks and returns to find the most profitable strategies. PSO is also valuable in more advanced fields. In robotics, it helps with path planning and coordinating multiple robots. Energy management companies use PSO to optimize energy production and distribution, while AI researchers use it to train neural networks, making it an essential tool in machine learning. In PSO, each particle represents a potential solution within the search space. The position of the particle is its current state, and its velocity determines how it moves towards the optimal solution. Particles adjust their velocity based on their own experience and the experience of their neighbors, which helps them explore the solution space more effectively. There are three key parameters in PSO. The cognitive coefficient represents how much a particle is influenced by its own best solution, while the social coefficient represents how much it follows the best solution found by the swarm. Inertia weight determines how much the particle's previous velocity affects its current movement, balancing exploration and exploitation. PSO begins by initializing particles with random positions and velocities. Each particle's position is evaluated using a fitness function, which determines how good the solution is. The particles then adjust their movement based on this evaluation. Next, the particles update their velocities using the cognitive, social, and inertia components, taking into account their own best solution and the swarm's best solution. They then move to new positions based on their updated velocities. This process is repeated until the particles converge on the best solution.
The velocity update equation is a crucial part of PSO. It allows each particle to adjust its velocity based on three key factors: its previous velocity, the best solution it has found so far, personal best, and the best solution found by the entire swarm, global best. The inertia weight, W, balances between exploration and exploitation, while C1 and C2 influence how much a particle is pulled toward its personal best and the swarm's best solutions, respectively. Once the velocity is updated, each particle's new position is calculated by simply adding its updated velocity to its current position. Over time, this iterative process helps the particles converge toward the best solutions in the search space. The inertia weight, W, plays a pivotal role in determining whether particles explore more broadly or focus on fine-tuning their current solutions. Higher inertia weight encourages exploration, while lower inertia weight helps the swarm to exploit the best-known areas. The cognitive coefficient, C1, ensures that particles remember their personal best, while C2 ensures they follow the swarm's collective knowledge.
PSO usually stops when the swarm has converged. This happens when particles' velocities and positions stop changing significantly between iterations. Alternatively, the process may halt after a set number of iterations or when the objective function reaches a satisfactory value. In the manufacturing industry, a key challenge is reducing production costs while maintaining efficiency. Variables like limited raw materials, fluctuating labor costs, and machine operational constraints complicate the problem. Our goal is to use particle swarm optimization, PSO, to find an optimal solution that minimizes costs while meeting production goals. PSO is an ideal algorithm for optimizing production costs because it can efficiently explore the entire solution space. Each particle in the PSO represents a different potential production plan, accounting for variables like material usage, labor distribution, and machine time. These particles learn from both their own experiences and the best solutions found by the entire swarm. We begin by initializing each particle with random values for key production variables such as material consumption, labor allocation, and machine usage. Each particle has a position, which represents a current production schedule, and a velocity that guides its movement toward improved solutions. Each particle's solution is evaluated using a fitness function that calculates the total production cost. The lower the cost, the better the solution. This fitness function helps guide the particles toward more cost-efficient production schedules. Next, the particles update their velocities using this equation. Velocity is updated by three main components: the particle's current velocity multiplied by an inertia weight, the difference between its personal best position and current position, and the difference between the swarm's global best position and its current position. This allows particles to gradually improve their solutions based on both individual and group performance. Once the velocity has been updated, the particle's position is recalculated using the position update equation. Essentially, this step moves each particle to a new production schedule based on the new velocity, guiding it toward a more cost-effective solution. The PSO process repeats for several iterations, with particles updating their velocities and positions until they converge on an optimal production schedule. The final solution is one that minimizes production costs while respecting all the constraints, providing a practical and efficient way to optimize industrial production. Particle swarm optimization and genetic algorithms are both powerful metaheuristic algorithms, but they work in different ways. PSO uses particles that represent potential solutions, and these particles, flying through the search space, adjusting based on the best solutions found by individuals and the swarm. On the other hand, GA represents solutions as chromosomes and relies on evolutionary concepts like crossover and mutation to evolve toward optimal solutions. Simulated annealing (SA) and PSO differ significantly in approach. PSO is a population-based technique, leveraging the collective intelligence of particles to find solutions. In contrast, SA is inspired by the annealing process in metallurgy, where material is heated and cooled to remove defects. In optimization, SA probabilistically accepts worse solutions at the beginning to help the algorithm escape local minima, gradually honing in on the best solution as the temperature cools. PSO's strengths lie in its simplicity and relatively fast convergence, as it requires fewer parameters to tune compared to GA and SA. However, one drawback is its tendency to get trapped in local optima, especially for more complex problems with many peaks and valleys in the search space. Genetic algorithms are great at exploring diverse solutions, making them less likely to get stuck in local optima. However, they can be computationally expensive due to operations like crossover and mutation. Simulated annealing excels at escaping local minima, but it tends to converge slowly, particularly in the later stages as the temperature cools down, requiring careful tuning of parameters. Over the years, several variants of PSO have been developed to improve its performance in various optimization problems. Adaptive PSO, APSO, modifies key parameters like inertia and cognitive coefficients dynamically, allowing the algorithm to balance exploration and exploitation more effectively. Quantum-behaved PSO, QPSO, on the other hand, is inspired by quantum mechanics, giving particles a probabilistic behavior that enhances their global searchability. Adaptive PSO is particularly useful when the optimization problem has varying levels of difficulty across the solution space. As particles explore and exploit the search space, APSO adjusts the inertia weight dynamically. Higher inertia promotes exploration, while lower inertia helps fine-tune solutions. This adaptability prevents particles from getting stuck and improves convergence speed. Quantum-behaved PSO, QPSO, takes PSO to a new level by incorporating principles from quantum mechanics. In this variant, particles are not confined to traditional velocity and position updates. Instead, they follow a probabilistic distribution based on a quantum potential well. This allows QPSO to avoid local optima more effectively and explore the solution space more thoroughly, making it ideal for complex, multidimensional problems. The choice of PSO variant depends on the nature of the optimization problem. If the problem space is relatively smooth but requires fine-tuning, PSO is a great choice as it dynamically adjusts parameters. For more complex problems with numerous local minima, quantum-behaved PSO is more effective due to its enhanced global searchability, allowing particles to escape traps and explore new regions of the solution space. Particle swarm optimization has become a key tool in solving complex optimization problems. Its simplicity, flexibility, and ability to handle nonlinear, multidimensional problems make it applicable across diverse industries, from optimizing production processes in manufacturing to improving investment strategies in finance. One of PSO's greatest strengths is its fast convergence, allowing it to find optimal or near-optimal solutions quickly. It also requires minimal parameter tuning, making it easier to implement compared to algorithms like genetic algorithms or simulated annealing. PSO is particularly suited to dynamic environments, where conditions can change in real time, such as in robotics and network optimization. Looking to the future, PSO's role in fields like artificial intelligence and robotics is growing rapidly. It is already being used to train neural networks and improve the performance of machine learning models. In robotics, particularly swarm robotics, PSO helps optimize the coordination of multiple agents working together. Moreover, smart cities are leveraging PSO to optimize everything from traffic management to energy distribution. Looking ahead, we can expect to see more hybrid versions of PSO, combining it with other algorithms like genetic algorithms or simulated annealing to improve performance even further. Quantum-behaved PSO and other advanced variants are already being developed to handle even more complex optimization challenges. These advancements make PSO a key player in the development of autonomous systems such as drones, robots, and even smart transportation networks.
Thank you all for your attention and for joining me in exploring particle swarm optimization. I hope you found the presentation insightful and that you gained a deeper understanding of how PSO can be applied to real-world problems. By